Hi everyone, my name is, and today I'm going to be talking to you about an interesting problem that we had when we wanted to scale 3D tiles to the size of the globe. To understand why that is the case, I'm going to cover a little bit of background about who we are and what we do. So I work for a company called Sensat in London, and we like to describe ourselves as working for good. And the reason behind that is that what you may not realize is that the architecture, engineering, and construction, or AEC sector, as of 2022, I believe it was, actually accounted for over 37% of global CO2 emissions, which is a staggering proportion of the damage we're doing to the planet. So we take a mixture of photogrammetry data collected from drones or low-flying planes, even attached to the top of vehicles like cars, in combination with some of the CAD models and like CAD drawings you can see on the side. And we take all of that data and bring it together in a way that users can collaborate on and make better decisions about the things they're building. So they might realize that they've got some legislation issue where they need to build something that's exactly 4.2 meters away from this other thing. Or they might realize that the foundations are going to be in the wrong place, or believe it or not, in some cases, they might realize they don't even own the land that they're actually about to try and build on. So you get some really crazy things coming out of this. But essentially, we're trying to enable people to work in civil infrastructure for things like highways, for things like water or energy transmission. And one crazy case, even the UK's nuclear fusion research was quite cool. So to take a little bit of a look at our sort of like high-level architecture, this is kind of how we use the sort of VisGL stack. When I say VisGL stack, I really mean loaders.gl. We are probably a little bit unique in that we don't really use VisGL in the way that a lot of the other talks that have come earlier in the day have done. Rather, as you can see, the data that comes in from, say, a LAS file, which might be the point clouds, which is like your digital twin copy of the real Earth. Some of the CAD files and the vector files that we get come in, and everything is crunched into a 3D tiles tile set. In the browser, we use loaders.gl to decode those 3D tiles tile sets, handle the tile selection so we know which levels of detail we need to show to the user, and then we have a little bit of magic glue that goes into a 3JS renderer of ours. We've thought about the possibility of moving that over to deck.gl, but it is something that is not an entirely trivial process because we have some unusual use cases around annotations and things like you might have seen on the other screen where we have like emergency routes planned, where we don't want to occlude them if they're behind certain objects. So the layering of different pieces of data is a little bit non-trivial. But why did we want to do this? Well, we wanted to build terrain. So you might have seen in the first image how there was kind of a black void where case we had deliberately hidden the layers, but if you don't have access to photogrammetry data because it's either not been collected yet or it's just not the use case that you have, then you can't really see the earth and the place that you're working in. And that becomes quite challenging. So we wanted to build terrain, but everything that we serve is a 3D tiles tile set. So naturally, we want to build a terrain-based 3D tiles tile set. And there are some great options out there already, so why not try to use them? Well, deck.gl, as I just mentioned, comes with a few complications. It would require us to either find a way to integrate within 3JS as well, which would be actually problematic, difficult to maintain, and even require us to maintain a fork. Something for the future. Or we could use something like Google's photorealistic 3D tiles. But again, this is not quite ideal because its source is in EPSG 4326 or lat longs, which is not visualization CRS that we are using. For us, everything is probably for many people converted to WebMacator, and that comes with its own legal challenges of creating derivative works. And equally, the 3D tiles, as you can see, also contain a lot of building data. So if the user is trying to build something new in a place where they need to demolish an old building to do so, this data kind of conflicts with the models they'd be trying to see, and you wouldn't be able to like look at your building properly because you'd have the other old building still in the way. So we'd rather have a digital surface model rather than a digital terrain model rather than a digital surface model. So easy to confuse those two. I get them backwards. So how exactly does a tile set work in 3D tiles? So to explain some of the challenges, we have to kind of understand a little bit about how 3D tiles works as a spec. And the really high level overview is that it is essentially a hierarchical level of detail structure. So that means that for every level that you go down, you get progressively more detail. When you start from the root, you have the most simplified version. And then we have a simple refined strategy, which is whether or not we either add the children of this tile to the visualization, so we render both the parent and the children, or we have a replace strategy like we would for terrain, where we, instead of rendering the parent, we just render the children. We determine whether or not we should render the parent or the children or children's children, so on and so forth, based on this geometric error value. And this is essentially a metric that determines the level of simplification between the original completely unsimplified version and the potentially highly simplified version that you might view from much further away. But the immediate obvious problem with this is that if you wanted a terrain set that had 24 levels of detail going through basically zoom 0 to zoom 24 of a standard Web Mercator set, that's about 33 million tiles. And that's going to be quite a big tile set, Jason. And you need to ship this to the client before you can start rendering any data. So if we were to try and send that, people would give up waiting before it even got there. We'd never show any data. Fortunately, as was mentioned in yesterday's talk, there is an implicit tiling scheme that helps to save some of the issues that we would have here. So rather than, as we had before, where you had like a child hierarchy, instead we completely get rid of that and we replace it with this implicit tiling structure instead. And that defines a subdivision scheme, which is either going to be a quad tree or an oct tree. So that determines whether or not you're dividing on the x and y axis, and you always divide in half in both cases. So you get 4 equal sized children. Or in the case of an oct tree, you also divide in the z-axis, and so you get essentially 8 equal-sized children. The number of available levels, which in our case would be 24, because we want to have the global tile of 0 all the way down to zoom level 24. It's kind of an arbitrary choice, but this is what we're using. And equally, a subtrees list, which is what this other piece of JSON is at the bottom. And this is how you get around not having that child hierarchy. So in the subtree, you would have, if you've ever seen GLTF or GLB, this is quite similar, where you have, say, like a bit stream here that it points to a buffer view, in this case, which is just another buffer that's an arbitrary piece of memory, and we're essentially reading bits of data out of that. So you determine whether or not the content or the tile is actually available at a given index, if that makes sense. So when you traverse through the quad tree, you can find a specific index, and if that value is a 0, it's not there. If that value is a 1, then it is there. Great. But again, 33 million tiles. If we need a bit for each one of those, that's still like 60 or 70 megabytes just to know which tiles exist. Fortunately, terrain is a bit easier because it's the globe. Every tile is valid. Every tile should have content. So kind of completely omit this. And you see that that's actually what I've done here with the tile availability. Using the constant value, we can actually send a very small subtree as well that just says, don't worry, the tile is always there, the content is always there. It's a constant value. There's no buffer whatsoever. So we've reduced what would have been this hundreds of megabytes worth of data into well, you can see it on screen. That's a big improvement. But this is not the end. Let's say that we've now got this to the client. How on earth are we supposed to generate a 33 million tile tree and then actually traverse through that structure in any kind of performant way? Every time you have to step through to a new level of detail and you have 4 or 8 children, you multiply and multiply, and it gets way out of hand way too quickly. So imagine that we start with some space that we're rendering in. And typically, when we're looking at how we want to render these things, we need to have a quick look at geometric error and how we would normally traverse a tile set like this. So typically, you might have an original unsimplified model and a very simplified version, which maybe we've done through mesh decimation. You basically selectively remove vertices, seeing which ones introduce the least error until you get something that is simplified. And in this case, I've overlaid the two of them on top of each other, highlighted these 2 blue areas on the top left and top right, where maybe the mesh decimation has been a little bit over eager. So we've got this noticeable gap. And the largest distance that you can travel in this gap is essentially the geometric error that we're highlighting there with the little red line. However, that geometric error, when we go to render it, depending on how far away the object is, we can convert it instead to a screen space error value, which is essentially the same geometric distance in meters, or whatever your underlying coordinate system is, but instead as a pixel space value. So we might know that this teapot has 10 meters of error. I don't know, that's a very big teapot, but here, maybe when you actually render it quite close to the screen, it has 50 pixels of error. That's a big deal. We don't want to show that. But if it's much further away, maybe it's only 3 or 4 pixels, and maybe that's acceptable. It's up to you to define exactly what your allowable screen space error is, but at the end of the day, it's kind of arbitrary. So we might start by loading the very, very basic, in this case, LOD2 representation. And when we look through each of these tiles, we look at, say, the center point, and we see that it is X distance from the camera. And we might decide that this left-hand side is a bit too close to the camera. So maybe we want to refine those into the LOD1 tiles. So we built these red boxes instead. And maybe the corner again further where the handle is again a little bit too close to the camera. So we need to simplify it a bit further, and we load the full level of detail for the handle. But this approach, as you can see, if we had to iteratively refine every single time we went down, we'd be there forever. We'd never finish refining the data. So this is where we had to get a bit creative, because unfortunately, there's not really a solution out there that already exists as far as we can tell. But if we go back to the space that we're in, rather than doing what we did before, where we had a model and we kind of like compared the model to the camera, what if we did things backwards and we actually took the camera space and we kind of compared that to the model, if you will? And this might sound a bit weird, but what if we could basically take this space that the camera can see, defined by the normal frustum planes, and calculate geometric error in that space, or screen space error in that space? And that sounds really bizarre, because you kind of then think, doesn't that mean we're solving some like complex mathematical function and like it's crazy? Like, surely that's not going to work. But a lot of things in graphics, you don't have to be correct. You just have to be good enough that no one can tell that you've not quite done the right thing. So instead, we can take a really naive approximation, and it turns out this is going to work really quite well. So imagine that we take a point that is right on the camera's near plane. So that's like right at the front of the screen in the dead center, and we use this as a close point. And we project that same vector some distance into the frustum. It doesn't really matter where, but we pick another point arbitrarily as our far point. And what we're going to do, rather than doing some crazy functional differentiation and all this stuff, we're just going to take a direct delta of the geometric error values at those two distances for the given tiles. And we just divide those by the distance between those points. And what this will give us, essentially a mapping of camera distance to geometric error. And as we walk along that camera vector, as we get further and further away from the camera, we can match up those geometric error values with points at which a given LOD should match the geometric error of that tile. And at that point, we know that we need to change to a specific LOD. And so on and so forth, we mark out those different points along our camera path. And this might arbitrarily tell us that from the red dots, we can get away with rendering zoom level 10. And from the blue dots onwards, we can get away with rendering zoom level 9, and so on, zoom 8, zoom 7, etc. This sort of slightly simplified top-down example will give us some really nice boundaries that we can then use to determine which tiles should be visible within those sections. So within the purple section, for example, we might take the coordinates that create the boundary of that, so the 4 corner points, the min and the max, if you will, and we can convert those into the tile space. Because we know, we've been given this invariant by the implicit tiling scheme, that every tile must be half the size of the previous, we can very quickly calculate how big a tile should be at zoom level 11. And we can immediately work out, okay, if the tiles are this big, then for us, this particular coordinate in world space must be at exactly coordinate 3 in X and coordinate 7 in Y. It's likely to be a non-round number, but we can round things off to get the exact tiles themselves. And if we do this for each of the different areas, we'll end up with something that's kind of starting to get close. You can see that it still has a few problems. So on the difference between the LED 11 and purple and red, hopefully these colors are showing up for everyone. I was worried that this wasn't going to work. You can see that there's a bit of an overlap. So there's part of the LOD 11 that overlaps into LOD 10. And if you were trying to render the terrain, you'd start seeing these weird situations where you've got two different levels of detail where they kind of overlap. And you've probably seen, sometimes you get Z fighting where you get flickering between the two layers. It can be even worse. So there's really one last problem we need to solve here, which is that we want to find where a given LOD has a boundary that matches up with its parent level. So rather than having this case where these three tiles on the right overlap halfway into LOD 10, we just want to make sure that it either aligns left side or to the right side. It doesn't really matter which way we pick. If we were to go closer to the camera, we would increase the detail, we'd decrease the detail that we are showing. So we'd have fewer tiles, but the error would be larger. So this would be a good approximation if you wanted to focus on performance for your rendering. Or alternatively, we can push those tile boundaries slightly further away from the camera at the cost of a bit of rendering performance, but we're going to get a nicer quality image. So kind of arbitrary depending on what it is you want to do. But in our case, we opted for visual quality over performance in this case. So we push the boundaries slightly away. And if we do that, we end up with something that looks a bit like this. So we've extended LOD 11 to cover a little bit of extra area. And you can see there are some places where we're kind of like wasting, so to speak. We are selecting data that's slightly outside the custom. In this case, LOD 9 is completely eclipsed LOD 8. It doesn't exist anymore. But this is kind of fine because doing this calculation is actually relatively simple in comparison to traversing this crazy tree. And so with that, we have the tiles we want. We can go and visualize a cool mountain or something. That's our terrain. It's ready for use in the real world. That's really all we had to do. And that's going to enable us to then take, for example, OSM maps and overlay some of the digital landscape data, such as the point cloud data. Maybe we can kind of make out this, what are they called? Wind power turbine things. Gone, like the building data, and we can start to build like a much more holistic scene where people can see all the data that they want to see. So this is kind of a little bit of a tale of how we came up against what we thought was going to be a limit in the 3D tile spec, how we overcame it, and hopefully, if this is something that is of use to other people, this is something we are very much willing to contribute back to the community. A couple of people I've spoken to have seen like they seemed kind of on board with that. So we're very happy to work with whoever to kind of get this sort of stuff added into loaders.gl. And yeah, I guess that's pretty much it for me. If there's anyone either on the recording or like a day later, you're like, oh, I wish I'd asked this question, feel free to grab links for contacting me later. Otherwise, I will hand it over for any other questions in the room. Yeah, I think I'm a tiny bit short on time, so maybe I'm picking up. But if anyone does have questions, that's great. I've either completely lost you or I've explained it so well.
My question is, so what you've described is essentially it seems like a swap and replacement for how Loaders does the 3D tile traversal at the moment, where you give it a viewport, you give it a tile set, you say, what do I load? Is that?
Yeah, essentially, the limitation that we were coming up against was that now that we had realized, oh, we could restructure our tile set and we could ship the data, well, we actually still couldn't use it. We did naively try to just see what would happen if we loaded it. Doesn't go very well. The browser will probably crash. So obviously not great for us. But yes, in theory, it's something that we could pretty much drop in as a replacement. But it is the kind of thing that I would see as probably wanting to be more of an optional, like opt-in feature, because obviously, if you've got a really simple example like that teapot with 3 levels of detail, you don't need this. This is overkill, and this is probably going to take more resource than it would to just iterate normally. But if you do have a big data set and you want to be able to render that as a tile set, then yeah, this is something that this is quite good for.
We should find a way to make the traversal algorithm pluggable in the GL and then you can attribute alternate.
Yeah, exactly. Something like that would be ideal, yeah. Okay, awesome. Well, thank you very much for having me.